In this video lesson, we're going to learn a little bit about nuclear power, which uses nuclear reactors to generate energy for power supply for residential, commercial, and industrial use. We will also learn about some of the hazards associated with doing so. So let's begin. Nuclear reactors use uranium-235, which is the fissionable fuel. So this is going to be a fission reaction. It powers the reactor. Now this uranium-235 comes from uranium oxide. Right. This is the ore. This is the rock that uranium atoms are in, and normally this uranium oxide is about less than 1% uranium-235, and the rest of it is other forms of uranium-238 primarily. Okay, it is uranium-235 is a fissionable fuel where uranium-238 is not, or not as easily done. So the problem is this is a pretty weak concentration. So this needs to be what is called enriched. And what we are trying to do is make it so that the ore is about 3 to 5% uranium-235. This is the percent uranium-235 that is used in the fuel rods of a nuclear power plant. Now, if we then take that and enrich it even more to 20+% uranium-235, this is what is used in nuclear weapons. Right? So let's talk about that a little bit. This fission reaction, right? You've got uranium-235, atomic number 92. This all starts with a neutron bombarding the uranium. That uranium then splits into two particles. It doesn't always have to turn into krypton and barium, but it oftentimes, this is what is used as the example to do this. So this is, krypton is 36, and let's see, barium is 56, plus 3 of these neutrons. So here's the thing, when this neutron hits this uranium and it breaks into these two particles, whatever, what's now what's interesting is what's going to happen to these 3 neutrons. If all 3 neutrons hit another uranium-235, so like these 3 now trigger 3 more uranium-235s, that's what is called a chain reaction. That's uncontrolled, and that can lead to an explosion. Or maybe that's desired if we're using it in a nuclear bomb. But if we can have only one of these neutrons trigger the next uranium-235, then we can control this reaction and not have it be crazy and get us into trouble. So these next 3 parts of the nuclear reactor are designed to control the rate at what happens with these 3 neutrons so that they don't just go crazy and trigger 3 uranium fissions. So what we have something called moderators, right? Moderators decrease the speed of neutrons. Moderators are made of either heavy water, meaning it contains the isotope hydrogen-2 instead of hydrogen-1, sometimes regular water, beryllium, graphite. These materials can help slow down the speed of the neutrons. If these neutron speeds are controlled, then they might not trigger the next fission event. Now, there are also control rods which absorb extra neutrons, right? So we can maybe just take some neutrons out of the picture, not letting all of these neutrons go on to trigger another fission event. We also have cooling towers to keep the temperature of the reactors cool and transport the heat produced by the nuclear reaction to the turbines for producing electricity. So let's focus on that. The whole point of using nuclear power, the power plant, the premise for a nuclear power plant works like this. Okay. what we have here, these are the uranium fuel rods. These are basically a bunch of pellets stacked on each other so that it's a really tall rod. And there's many of them inside of this pool. This is like a pool of water, which is used to kind of absorb any extra heat. That water does get heated up, right? And so water gets pumped through here. That water doesn't mix with outside water. There's outside cold water coming in. That cold water gets turned into steam. That steam is brought through a turbine, which is basically a giant fan. It spins the fan, which turns the generator, which produces the electricity. Okay. That water by now is super hot, so it has to go out here. That hot water has to cool down. This is a cooling tower, right? So there's lots of surface area here to allow the heat to dissipate. And then cold water is brought back in. That cold water is turned into steam. The steam turns turns the turbine, and electricity is generated. Okay, so there's two separate water sources. One stays within the reactor building, and the other water source is an outside water source. Okay, but the control rods, right, these are made of either boron or cadmium, and these can be lowered or raised depending on how fast we want the reaction to take place. Right, these control rods, when they slip down in between the fuel rods, they actually absorb neutrons and stop this fission reaction from happening. Okay, so that's the primary means that are used to control this nuclear reaction from happening. So they actually, it's like fitting, it's hard to describe, but yeah, there's just these rods that lower in between all the fuel rods. All right, now let's take a look at the shielding. The shielding that has to go around the building to keep people safe, right? Because those neutrons that are produced by the nuclear reactions, they're dangerous, right? We have to really shield even ourselves from them. So, because the crazy part is neutrons don't have any electric charge, so therefore they cannot be affected by electric forces. Like if it were protons can be slowed down by surrounding them with a negative charge. We can affect their path. But neutrons without any electrostatic charge are not going to be affected by that. The problem is when neutrons are absorbed by other substances, that produces gamma radiation. So we need to figure out how to shield ourselves against gamma radiation, right? Neutrons, when they are absorbed, make that matter radioactive, and therefore we have additional radioactive material to deal with. And so coming up to here, you see here, we've got alpha rays, which are stopped by paper, beta particles, which go through paper but are stopped by thin metal, gamma rays, right, go through paper, go through thin metal, but stopped by thick lead or steel. But neutron rays go right through, right? So there has to be a special type of concrete that I'm sure it's way more complicated than that, but there is a special material that is used to stop neutron rays from going into places that we don't want it. So there's extra precautions that have to be taken because the gamma rays produced are so highly energetic, and we don't want those impacting people. Now, besides the safety issues that go on with the operation of a nuclear power plant, the radioactive waste, where does it go when the uranium has been spent to a point where it's no longer concentrated and it is not able to produce the energy that we need? It's still radioactive, so we have to figure out how we are disposing of the radioactive waste. Right, so to avoid overexposure to humans and to prevent environmental pollution, spent nuclear fuel must be stored safely. This takes time to allow the radioactive waste to decay to products that are less hazardous to the environment and the living organisms within. Initially, the spent fuel rods will spend 1 to 2 years in a concrete and steel-lined pool of water. Afterwards, solid and liquid radioactive wastes are encased in storage casks and stored underground on site at the nuclear power plant. Ultimately, the idea is to bury the spent waste deep underground, but finding that site has been a long time debate and is ultimately an issue that needs to be resolved if we are going to continue using nuclear power plants to generate electricity. This is just scratching the surface, but this video lesson was meant to give you a quick view as to how nuclear power plants work, the nuclear reactions used and how we control them, and some of the issues involved with operating nuclear power plants. All right, that's it for now. We'll see you back in the classroom.